So let's look at some problems from chapter 5, all about gases. So the first problem we're going to look at is a balloon filled with helium has a volume of 4,000 liters at 25 degrees Celsius. What volume will the balloon occupy at 50 degrees if the pressure surrounding the balloon remains constant? Okay, so a few things here that's really going to help us out is whenever it says something remains constant, so in this case the pressure is remaining constant, that means we don't need that variable, okay? So we don't need P in there at all. So I'm going to start by writing my knowns and unknowns. So I'm going to make a list because that will help me figure out which equation I want to use. So I'm going to start with this 4,000 liters. Now that is a volume. Okay, the next piece of information I see is 25 degrees Celsius. Now that is going to be a temperature. For both of these, I'm going to label them VI and TI because they go together, because the volume is 4,000 liters when the temperature is 25 degrees Celsius. So that's why they're both going to have I's by them for initial volume and initial temperature. The last piece of information, it's saying, okay, well, what is the volume going to change to if we increase that temperature? So my final temperature is going to be 50 degrees Celsius. And they're asking, once it's at 50 degrees Celsius, what's my new volume going to be? And when we looked at the relationship between volume and temperature, if the temperature goes up, the volume should also go up. Okay, so we should expect it to be higher than 4,000 once we solve for our final volume here. All right, so looking at equations, the equation that's going to work for me is Charles' law. So VI over TI is equal to VF over TF. Okay. Because I have VI, TI, and TF, and I can solve for VF. So I need 3 out of the 4 variables. I have 3 out of the 4, and I can solve for the 4th one. Before I can use this equation, though, we need to convert. Okay, volume's fine because we do want volume in liters, but what do we want temperature in? We don't want it in degrees Celsius, but we want it in Kelvin. So if you remember back from chapter 1, just going to write the equation down here. To get Kelvin, you take degrees Celsius and you add 273 to it. Okay, so that's what I'm going to do to both of these. I'm just going to add 273 to get my new temperature in Kelvin. Got my calculator. So 273 plus 25 be 290. 298. And then 50 plus 273. So 323. Hopefully I'm doing these calculations right. So I got Kelvin, I got Kelvin. Now that everything's in the correct units, I'm going to go ahead and I'm going to rearrange this equation here so that I have VF all by itself on one side of the equation, all the other variables on the other. Okay, so if I want VF by itself, I need TF to be over here. So since TF is in the denominator, I'm going to multiply this side by TF because TF divided by TF cancels each other out, right? They're on opposite sides of the horizontal line. Whatever I do to one side of the equation, I have to do to the other. So I'm also going to multiply the other side by TF. So what this does is it cancels it out on the right side of the equation, leaving VF by itself. And then this side becomes TF times VI, and all of that is divided by TI. So now I can just plug in my variables in the correct units and solve. So let's see what I get here. So my final volume is going to be 298 multiplied by VI 4,000. And all of that divided by my TI. Oh, already made a mistake. My TI is 298. Let me go ahead and erase this. Because TF was 323. So make sure that you're looking closely at those variables. Okay, so I'm going to take 323, multiply it by 4,000, and then divide that by 298. Now I expect the volume to go up because the temperature goes up, volume goes up. They're proportional. And I get 4,335.57, etc., etc., etc. Well, let's look at significant figures. So 1, 2, 3 there, 3 there, and then a whole bunch there. So I want 3 sig figs. So 1, 2, 3. So I'm going to stop here. Look to the number next to it. Does that stay a 3? It does not. It's going to move up to a 4. So we have 4, 3, 4. But I can't just stop there because I need it to be 4,000, not 400. So what I'm going to put in place of this 5 is a 0 because that will not count as a significant figure, but it counts as a placeholder, making sure that I'm staying at the same magnitude. Units are going to be liters. So let's double check. We expected the volume to increase since the temperature increased, and it did. It went from 4,000 up to 4,340. Let's try another one. So now we're going to calculate the volume of N2 that results when 0.1 liter of gas is heated from 300 K to 350 at 1 ATM. All right, so let's start with our knowns and unknowns. So we have 0.1 liters, that's a volume. It's heated from 300 to 350. Okay, so the temperature that goes with that initial volume is 300 K, 300 Kelvin. So I'm going to label these both with an I. So I have an initial volume of 0.1 liters at 300 K. It's asking for the new volume when we heat it up to 350. Okay, so we're increasing the temperature yet again, just like in the last problem. So if we're increasing the temperature, what do we expect the volume to do? We expect it to go up, right? So they're proportional to each other. So this time I'm using the same equation that I used in the last problem. VI over TI is equal to VF over TF. I'm going to look at my knowns, make sure nothing needs to be converted. We got liters and we have Kelvin for temperature, so everything looks good there. And we are solving for VF once again. So we're going to rearrange that equation to show, get VF by itself on one side of the equation. Okay, so if I want VF by itself, I need to get rid of this TF. Since it's in the denominator, I'm going to multiply by TF on both sides of the equation. Over here, it's going to cancel out because I have TF over TF. They're on opposite sides of that horizontal line, so they cancel. So now we have VF by itself, and we have TF multiplied by VI over TI. Just showing how that equation is rearranged once again. Once you have it rearranged, plug in your values. See if I can get them in the right spot this time. So we have the final temperature on top, so that's 350. We're going to multiply that by the initial volume, which was 0.1, and then divide that by the initial temperature, so we're looking at the 300 on the bottom. All right, so calculating this out, we have 350 times 0.1 divided by 300. 1166666666. And then a whole bunch of sixes. So let's look at significant figures. We got 3 there, 4, and 4. So we want 3 sig figs, SF. So 1, 2, 3, look at the number next to it. Does it stay a 6? It does not. It's going to move up to a 7. So we get 0.117 liters. Because it is a volume, so that's why the units on it are going to be liters. Now we expected, since the temperature increased, that the volume would also increase, and it did. So we have a sample of helium gas, volume of 1.27 liters. At a certain temperature, 5 atm. We're going to be compressing this gas now. So the volume is going to go down and the pressure is going to go up, and it wants us to calculate the temperature, the final temp. How much does it increase? All right, so let's do our knowns and unknowns so we can find the appropriate equation. So first piece of information given, volume of 1.27 liters. Then we come across 149K, and that is what? Kelvin, it's a temperature. 5 atm. That is a pressure. So all of these conditions are the initial conditions. We have 1.27 liters initially at this temperature, at that pressure. So I'm going to write I's by all of those so that I know those all belong together. Now we're going to change the conditions, and the gas is going to be compressed to 0.320 liters. So that's my final volume, so V sub F, at 50 atm, atm being a pressure, final pressure. Run out of room. And they're asking, at these new conditions, the temperature is going to increase, and it wants us to calculate that final temp. So TF, question mark. All right, so looking through my equations, I need equations that have all of these variables in them. Okay, and the equation that's going to work for me is the PI VI over TI is equal to PF VF over TF. So I have all variables except for TF. So this is what I'm trying to solve for. So I'm going to rearrange this equation so that TF is all by itself, and everything else is on the other side of that equal sign. All right, well, I have TF in the denominator. That's just not going to work for me. I need it in the numerator. Okay, so my first step is going to be multiplying this side by TF because I want to get it out of the denominator. It needs to be on top. If I multiply this side by TF, I'm actually getting rid of it on this side, but that's okay because whatever I do to one side of the equation, I have to do to the other. So I'm also going to multiply the other side by TF. So even though it cancels out over here, it's now in the numerator on the other side of the equation. Okay, so I have TF times PI VI over TI. And over here, I have PF VF. All right, so I still want TF by itself, so I need to get rid of all that other stuff. Okay, so to get rid of it, I can multiply by the reciprocal, but I'll show it stepwise, just in case you don't know what multiplying by the reciprocal is. So if I want to get rid of TI, right, it's in the denominator. So to get rid of it, I'm going to multiply, because TI over TI will cancel. Whatever I do to one side, I have to do to the other. Okay, so by multiplying by TI, I get rid of it on this side, and I bring it up over here. Okay, so now I have TF PI VI, and then I have PF VF times TI. Okay, so I'm still trying to get that TF by itself, right? So I need to get rid of PI and VI. Since they're in the numerator, right, they're on top, I'm going to divide by PI VI. Whatever I do to one side, I have to do to the other. So it's going to cancel it out on this side, finally getting TF by itself, and then putting it in the denominator on the other side of the equation. So my rearranged equation, I'm using the whole board for this one, it's going to have final pressure, final volume, initial temperature, divided by initial pressure and initial volume. So let's plug in our information and solve. The easy part, right? Once you have it arranged. So I'm going to need, my final pressure is 50. My final volume, 0.320. My initial temperature, 149. On the bottom, my initial pressure was 5. My initial volume, 1.27. So let's plug all that in. And it's looking like we're going to need 3 significant figures for our answer. So we have 50 times 0.320 times 149. Divide that whole thing by 5 times 1.27. So I get 375. What are the units? It's a temperature. So it's going to be Kelvin. So it told us that the temperature increased, and it did. It went from 149 Kelvin to 375. So that's just a nice check to make sure you did the problem correctly and that you plugged things in and rearranged the equation appropriately. Okay, temperature increased, so at least we have that going for us. Hopefully I did it right. So we have 5.5 moles of carbon monoxide occupying 20.6 liters. We're going to calculate how many liters if we increased the molar amount. Okay, so we're talking moles. So you can guess it, we're using Avogadro's law here. So let's write our knowns and unknowns. We have initially 5.5 moles. And remember, the variable for moles is that letter N, lowercase n, okay? That 5.5 moles is going to occupy a volume of 20.6 liters. So I know that's a volume because of the units, all right? These two go together, so I'm gonna label them as I's. That's my initial molar amount, my initial volume. Now the question's asking how many liters. So we need another volume here. So how many, that's our question mark, that's what we're solving for, if we had 16.5 moles instead. So this being our final molar amount, 16.5, what will be our final volume? So if we're increasing the number of moles, I would expect to see an increase in the volume. More moles you have, the more molecules, the more atoms, so it would take up more space. Now notice it's saying at the same temperature and pressure, okay? Whenever temperature and pressure are constant, or when they're the same, all that means is you don't need those variables, okay? That's why we don't need to write a temperature over here or a pressure, because it's remaining constant, it's not going to come into play, right? So the equation we have for this is VI over Ni is going to equal Vf over Nf. And we are solving for final volume. Okay, so we want final volume by itself, so we need to get rid of Nf, final moles. So to do that, since it's in the denominator, I'm going to multiply by Nf. That will cancel it out on this side. Whatever I do to one side of the equation, I have to do to the other, so I'm going to multiply this side by Nf as well. That is going to get my final volume by itself. I'm going to have Nf now is in the numerator, multiplied by Vi, and that whole thing is divided by this Ni. So let's plug in. We have a final molar amount down here of 16.5. We have an initial volume of 20.6. and the initial molar amount was 5.5, so that's going to go in the denominator on the bottom there. Okay, so when I multiply that out, we're looking at how many sig figs this time? 3, so 26, and then divide that whole thing by 5.5. So 3 sig figs, I get 61.8. What are the units? It's a volume, so it's liters. Now it's nice to double check, right? Our molar amount increased. So if our moles increased, that means our atoms, our molecules increased. Okay, so if we have way more molecules, what would we expect for our volume? More molecules take up more space, so I would expect a higher volume. Did the volume go up? Went from 20 up to 61.8. Indeed it did. So calculate the number of moles of helium in a 1 liter balloon at 27 degrees Celsius and 1 atm of pressure. Okay, so you'll notice this one's a little bit different than the last few problems that we've looked at. Why? Well, notice they have a volume, a temperature, a pressure, and they're asking for moles. But notice there's only one of each. In all the other problems we've been doing, there's been 2. That's why it's been necessary for us to label them as P sub I and V sub F, so that we could differentiate between the 2. But this time there's only one of each. Okay, so that's your first clue that we're going to be using the ideal gas law. But I'm going to start, like I always do, with my variables. So this 1 liter, that is a volume. And since there's only one of them, one volume, I don't need to put sub I or sub F or anything like that. Okay. The next piece of information, 27 degrees Celsius. That is a temperature. Take note, it's in Celsius, so I'm going to need to convert that before I put it in any of my equations. Okay. And then last but not least, we have 1 atm. That is a pressure. And what is it asking us to solve for? Calculate the number of moles. So it's asking us to solve for N. All right, so the only equation that's going to work here is our PV is equal to nRT. So P we have, V we have, N we're looking for, R, so we need our R value, and remember that's a constant that is given to you on your equation sheet. So I'm just going to add that over here, leaving it unitless. Kelvin moles, you can do it. All right, so adding that so it's ready for when I need to plug it in. Before I plug in though, I'm going to rearrange this equation to solve for N. So I want N on one side of the equal sign and all the other variables on the other. Okay, so I need to get rid of this R and T. So to get rid of them, since they're in the numerator on top, I'm going to bring them down on bottom. So I'm going to divide by RT. That's going to get rid of it on this side of the equation. Whatever I do to one side of the equation, I have to do to the other. So cancels out over here and then remains in the denominator on this other side. Okay, so I have N is equal to PV divided by RT. So now let's plug in. My pressure is 1 atm. My volume is 1. My R value is that constant, that's 0.8206. And then my temperature, I didn't convert it yet. So, glad I noticed that. Let's go over here. Remember, to convert from Celsius to Kelvin, all you do is add 273. And I believe that's going to give us an even 300. All right, so plugging in, don't forget my units, 300K over here. So I'm going to have 1 times 1 on the top, divided by 0.08206 times 300 on the bottom. How many sig figs are we looking at? I'm seeing 2 because of that guy there. So for 2 significant figures, I'm going to get 0.041 moles. So very small amount. Calculate the volume of 0.35 moles of N2 at STP. Okay, so remember STP stands for standard, temperature, and pressure. So by using those three letters, STP, they're giving us the temperature and the pressure. All right, so calculate the volume. So that's what I'm looking for. 0.35 moles. Remember, that's represented by that letter N. Standard pressure is 1 atm. And standard temperature, 273. So I have just one of each variable, so we're using the PV is equal to nRT again. So we need that R value, that constant. And this time, we're solving for volume. So we want the V by itself. So to get the V by itself, we got to get rid of the P. It's in the numerator, so we're going to divide by P on both sides. It's going to cancel it out on the left side of the equation, leaving V by itself. We have nRT divided by P. So plug in what we have, our N, the number of moles. Keeping with my units here. So 0.35. My R value, 0.08206. My T is 273, standard temperature conditions. And my pressure is just 1. So I get 0.35 times 0.08206 times 273. So what volume do I have? 7.84, but we're looking at just 2 sig figs. So I'm going to do 7.8, and what are the units on volume? Liters. So 0.35 moles will take up 7.8 liters of volume at standard temperature pressure conditions. All right, so let's look at another problem. So in this problem, they're talking about tires. So the volume's remaining constant. You'll see this last sentence here. So the tires on my bike have a pressure of 1.35 atm during the summer, when the average temperature is 315 Kelvin. During the winter, the pressure in my tires dropped due to the temperature change. You'll notice this oftentimes with your vehicle, your car as well, is that come winter time, you need to add air to your tires because of that temperature change. So here is a calculation we can do to figure out what that new temperature is in the winter. Okay, so I'm going to start with my knowns and unknowns. So the first piece of information given is this 1.35 atm. That is a pressure. And then that pressure of 1.35 is when the average temp is at 315. So I also have a temperature. Okay, since I have 2 pressures in the question, I need to differentiate them. So I'm going to label these PI and TI. Those are my initials. And then during the winter, the pressure changes. So I'm going to put that as PF down to 1.10 atm due to the temperature dropping. So we're going to calculate the new temperature that caused this pressure change. So that'd be my TF. Now notice when you look at your equations, we don't have an equation that has just these 4 variables in it. Okay, what we do have is this equation, PIVI over TI is equal to PFVF over TF. And we can actually use this equation because notice this last sentence. It says the volume remains constant. And I said whenever a variable remains constant, you can get rid of it. Okay, so if the volume is remaining constant, that means I can use this equation and just not take the volume out. Why can I do that? Okay, well, let's give it an arbitrary amount. Let's say the volume is 1 liter. So if I put 1 liter on this side, I'm also going to have it on that side. So that's why they cancel, right? Say the volume was 5 liters. Well, I'll have a 5 on this side, but I'll also have a 5 on that side. So that's why I can cross it out, because they're going to cancel each other out anyway. Okay, because they're constant. It's the same number on both sides of the equation. Okay, so by taking out that volume, my new equation becomes PI TI is equal to PF TF. So now I can use the information I have and plug in. Before I do that, let's rearrange this equation further, because TF is what I'm looking to solve for. So I want TF by itself. So to do that, I'm going to multiply by TF, because I don't want it in the denominator, I need it up in the numerator. Do that to both sides of my equation here, cancels out on that side. So I have TF PI over TI, and then PF here. A couple different steps. So I'm still looking to get TF by itself. Okay, so to get rid of TI, since that's in the denominator, I'm going to multiply to get it up in the numerator. It'll cancel on this side. And I have TF PI now on the left-hand side of the equal sign, and I have PF times TI on the right-hand side. So one last step to get that TF by itself. I need to get rid of PI. It's in the numerator, so I'm going to divide by PI. Make this a little bit more clear. PI over PI cancels out. Whatever I do to one side, I have to do to the other. So I'm going to divide the other side of the equation by PI. That will give me TF by itself. And this is what my rearranged equation will look like. So plug in, PF is 1.1, TI is 315, PI is 1.35. Bigger board. All right. So 1.1 times 315 divided by 1.35. And I get, how many significant figures are we looking at? 3. So 257. And it's a temperature, so the units are going to be K for Kelvin. Okay, so the original question said that during the summer, we had an average temperature of 315. So during the winter, we would expect the temperature to go down. Did it? Yes, it did. Went down from 315 in the summer down to 257 in the winter. So the key with this problem is recognizing that the volume remains constant and that you can use this equation and take out the volume piece because it remains constant. It'll be the same on both sides of the equation.